performance test and heat balance over 4-stroke single-cylinder diesel engine with electrical loading. This is the test rig used for this experiment. Diesel engine, and the rated RPM is 1500. As we can see, the crankshaft of the engine is connected to the generator shaft. This is the AC generator. It has a capacity of 7.5 kVA at 1500 RPM and a power factor of 1. These are the air heaters used for applying electrical load. This is the air box with orifice which is connected to the engine intake manifold through this pipe. This is the exhaust pipe which is connected to the heat exchanger. Cooling water supply. As being shown, it is connected to the engine head as well as the heat exchanger. These are the two water meters used for measuring the flow of water. These are the loading switches, each of 0.5 kilowatt. These are the voltmeter and the ammeter. Energy meter. Engine speed indicator and the temperature indicator. Temperature selector knob. This is the U-tube manometer which is connected to the air box to measure the airflow across the orifice. Observe the blue colored water in the manometer for reference. The visible fuel tank has a capacity of 7 liters. This is the pipette which is used to determine the fuel consumption. The start point and end point are marked on the pipette for measuring 10 cc of fuel. Now let's open the water supply valve and start the experiment. Close the exhaust valve initially. Now insert this hand crank into the camshaft as being shown. Holding the exhaust valve, crank the engine. As the engine is about to start, open the exhaust valve. As we can see, the engine is now in running condition. Switch on the console. Using the load switch, apply a load of 0.5 kilowatt. Note down the ammeter and voltmeter readings. Note down the engine speed. Calculate the difference in the manometer reading. Closing the fuel supply knob and using a stopwatch, check the time taken for fuel consumption from start point to end point on the pipette. Observe the energy meter and note down the time taken for 3 revolutions. Now note down the temperatures T1, T2, T3, T4, T5, T6 and T7. Using the second load switch, apply an additional load of 0.5 kilowatt. Note down all the readings as been done previously. Now again apply additional 0.5 kilowatt load. In this manner, as being shown, we have to repeat the experiment up to 2.5 kilowatt load has been applied. After all the readings have been observed, tabulate the values respectively. Note down the time taken for the flow of 1 liter of water through the engine head as well as the heat exchanger as being shown. Release the load by switching off all the load switches. Press and hold the fuel cutoff to eventually stop the engine. Using the tabulated values, calculate the performance and draw up the heat balance sheet. This concludes our experiment.
Hello students. Today I am going to discuss about how to draw the heat balance sheet for a 4-stroke diesel engine. I will demonstrate the procedural aspect, theoretical calculations, and taking the values. One specimen set of calculation also I will show for all of you, so that you will be comfortable when we give the values for to evaluate as a ATD lab test. So you can do the calculations. And once we do the calculations, you can draw the graphs of different parameters. So let's start. So first we have to conduct the performance test on 4-stroke diesel engine and draw the following graphs, including heat balance sheet. This is our setup where we have engine, the number 9 stands for engine, and air will be supplied from air tank number 8, and fuel will be supplied from a burette number 3. This pipette has been mentioned here. So fourth is called fuel tank. So for the engine, air is supplied from the air tank number 8, and fuel is supplied in a prescribed amount through burette number 3, and burette is supplied from the fuel tank. So this is how the setup is basically. And as engine runs, it is connected to the coupling to the row brake dynamometer 11. So through this, its engine output can be measured using the dynamometer. And there is a backside engine. You can see in the figure there is an engine in the figure 2. So in the engine you have exhaust gas, and exhaust pipe through which exhaust gas goes out, and there will be a coolant water supply over the engine, and also there will be inlet air and fuel mixture supply. This is a diesel engine, so only air will be supplied to the engine. So all these things now, using the manometer, how much amount of water is supplied to the engine as a cooling water jacket is measured, and two is what is the RPM of the engine brake drum RPM. So that can be measured through digital speed indicator, and one is manometer, and fifth is the temperature channel indicator, where we have different channels. So for example, if this I consider as an engine, just follow me schematic, I'll show you. If this is our engine, so this is the exhaust gas, and this is the inlet pipe, and consider there is a water jacket. Just as a schematic. So now how much water is supplied is at what temperature, TW1. Because of engine hotness, heat is absorbed by the cooling water and it goes with the water TW2. TW2 is greater than TW1, and amount of water supply is mass of water. Similarly, exhaust gas. So exhaust gas at the exit, you will get exhaust gas temperature higher, and inlet you will get, this will be connected to the kind of heat exchanger. And in our lab we have a setup called calorimeter. So how exactly it is done? Like this. See now, this exhaust gas is connected in a calorimeter, where calorimeter will have water supply. So exhaust gas temperature is absorbed by the calorimeter, and calorimeter water temperature can be equated to the amount of heat taken away by the exhaust gases through the engine. So this is how the overall schematic looks like. Anyway, I will describe in detail as we proceed on. So next you see a specification of the engine. So we have 4-stroke diesel engine. It's a Kirloskar made, and 5 HP is the rated power output, and maximum 1500 RPM. And generator can generate 10 kVA and 3 horsepower, and 440 volts, 50 hertz, and engine having 85 mm bore and 110 mm stroke, and compression ratio is, it can be operated till 16.5:1. Cylinder capacity is 553, and it is a manual cranking operated system. You have to start with by hand cranking, and orifice is 15 mm. Orifice is comes when air you are supplying. So the amount of air, as I mentioned here, this is a fuel tank and this is a air tank. So in the air tank, here in the air tank, okay, so air is coming from the atmosphere through the orifice connected to the tank. So that orifice diameter is 15 mm. So that through that orifice we can quantify the amount of air entering the tank, and through which it enters the engine cylinder. So everything has to be quantified. So as a recapitulation, so engine is operated by the fuel and air. Okay, so air is quantified by the burette, and fuel is quantified by the burette, and air is quantified by the orifice, and engine operations are quantified by the dynamometer, and the engine connected with the cooling water, and exhaust gas connected to the calorimeter. So all these TW1, TW2, and this gas temperature TG1, TG2, exhaust gas temperature, inlet gas temperature, are measured in the temperature channel selector. So this is a where directly we can get the reading of these thermocouples where it is connected. Okay, so this is how it operates. Let's see how exactly the procedure. So you have to check the diesel and keep the first lever in neutral position, then ensure the water supply and pressure sensor operation, cooling head and exhaust gas calorimeter, and start the engine by operating the cranking lever. And once crankshaft runs, the engine starts, and apply the load using the brake drum in the brake drum dynamometer, and put the spring balance to its operation. Then allow the fuel through the burette and note down the all these things. So for 10 cc of fuel consumption, okay, actually in our calculation it is 20 cc, so we can consider this one as 20 cc. So for 20 cc of fuel consumption, how much time it has taken, and how much load you have applied, and what is the manometer reading, speed of the engine, temperature of inlet air and exhaust gas, and water meter, exhaust calorimeter. So repeat the experiment for different loads and calculate all these parameters. So don't worry, this is just procedure I'm briefing, but when I show the calculations, it will be very clear to you. Even formulas also, I'll describe one by one. So head of the air, so has to be converted because manometer, okay, manometer, it shows head of water. Okay, so this how much air is supplied, and through the orifice, actually through the manometer we will get how much water head is collected. So that is head of water in the manometer, so that you have to convert into head of air using this balance equation. So head of air equal to rho of water and head of water into rho of air. Now through this mass of air, now mass of air calculation is the discharge rate of air and rho of air. Discharge rate of air, as I said, you have to use the coefficient of discharge of the orifice in the tank. There is orifice, there is a specific coefficient of discharge of that orifice. Using that, you have to measure the discharge rate. So pi d square by 4 into coefficient of discharge of orifice, and 2g HA. HA is head of air, calculated here. So basically, this manometer is used for calculate the head of air, head of air in terms of water head. That you have to convert in terms of air head. Okay, so cooling water flow rate will be directly calculated by in terms of liters per minute using discharge meter, not manometer, as I prescribed earlier. So next you see mass of fuel is very straightforward. So burette volume is 20 cc, as I said. 10 raised to minus 6 you are converting in terms of meter cube, which is there in centimeter cube. I think it is mm cube. So you are converting in terms of meter cube into density, rho into volume divided by time. So that gives the mass fuel rate of the diesel. And air fuel ratio is mass of air to mass of fuel. Brake power is 2 pi nt divided by 60,000. So nt, torque is applied spring balance load into radius of the brake drum. Okay, so spring balance reading, I'll show you how to calculate, and the radius is the brake drum radius. We'll get the brake power. Specific fuel consumption, you know, mass of fuel, how much you have supplied and how much brake power it is generated, that ratio. Input energy is mass of fuel into calorific value of the fuel, diesel. So mass of fuel you have calculated here. Mass of fuel you have calculated here at the beginning, mass of fuel. Then calorific value of the diesel you just multiply, you will get the total input energy. Indicated power, so indicated power is brake power plus friction power. Friction power from graph you have to calculate. How to calculate friction power, I'll show you here. See now, as for different experiments, you will calculate brake power and you will get fuel flow rate for different trials. And if you draw the graph will intersect the y-axis and it will cross. And when it intersects the horizontal axis, so from here to here, this is called the friction power. So friction power plus brake power, that total is called indicated power. Okay, so this you have to do when we give more number of trials, 3-4 trials, then calculate this value, draw the graph, fuel flow rate versus brake power, then that line when it intersects with the horizontal axis line with reference to the y axis, so this is called the friction power. Okay, so this is what it is mentioned from the graph. I will anyway calculation I'll show you, don't worry. So now brake thermal efficiency is brake power divided by how much input energy you have supplied. Indicated thermal efficiency, indicated power, and how much input energy you have supplied. So input energy you have already seen, MF into CV. Mechanical efficiency is, you know already, brake power divided by indicated power. So actual air supply is mass of air divided by rho of air, and volumetric efficiency is Q actual divided by swept volume. These are all things we'll see in the calculations. Okay, heat balance sheet. Yeah, so now directly I'll take the values, then I'll go with all these calculations. So I'll take the value which you have performed the experiments. So this is what tabular column looks like. Now we see. So I'll consider engine speed is 1500 rpm. One set I'll just consider spring balance reading 4 and 0.2. So F2 left side arm, right side arm. So left side it shows 4 kgs and left side it shows 0.2 kgs. And fuel burette, as I said, we are always consider the 20 cc. To flow 20 cc, it has taken the time around 100 seconds. Okay. And calorimeter, the exhaust gas goes with the calorimeter. Calorimeter inlet water temperature is 22 and outlet water temperature is 28. So water absorb the exhaust gas heat. And engine head, this is cooling water jacket temperature, is input is 27 and output is 32. And exhaust gas actual temperature is, inlet temperature will be very high, about 300 degrees Celsius, whereas it has cooled down to 70 degrees Celsius. Okay, by the calorimeter. Now air inlet temperature is atmospheric 26 degrees Celsius, and air flow rate, air manometer reading, which gives 9.5 in mm of water. Okay, and then water flow rate in liters per minute is 2 liters per minute. And cooling water, one thing is missed here, so hence I will include that also. Okay, so here cooling water to the calorimeter. So that rate, it's in liter per minute, again liters per minute pm. So that is 3 liters per minute I am considering. So now I am taking this value and I will show you the calculations one by one. And once you calculate, you have to fill entire this tabular column. Anyway, I have taken one value. I'll show you for only one value. So similarly for your test, we may give 3-4 values. So that you have to calculate. Let's consider this. Okay. So come back to our calculations one by one. Here itself, I'll show you. So now head of air. Okay. So here itself, I'll show you. So head of air is now rho of water is 1000 into head of water. So head of water, you see this tabular column. So head of water is yes, a manometer. Manometer is 9.5 mm. Okay, so 9.5, it's in mm, and into 10 raised to minus 3. Anyway, I'll just put it in mm divided by rho of air. So what will be the rho of air? Maybe it is 1.2. Okay, so maybe I'll consider mm, 1000 mm equal to 1 meter. So hence 9.5, 1 mm equal to 1 divided by 1000. So 1000 into rho of air is 1.2. I'm considering. Okay, so if you do this, you will get 1000 will get cancelled, this thing. So 9.5 into 12, 9.5 into 12. So you'll get okay, so you'll get 9.5, and the density of air, okay, 9.5 into 12, sorry, 9.5 into 1.2, so 11.4 meter of water, meter of air, sorry, 11.4 meter of air. Now it's in terms of meter of air. Next, you should calculate the mass of air. Mass of air is discharge rate of air into rho of air. Discharge rate of air is, here you check out the given value. The discharge air is airflow rate manometer reading, and here it is a calorimeter. Yeah, so this directly we have to put it in terms of CD, pi by 4, D naught, all these values you have to put forth. Q of air through the orifice using this standard formula. 11.4 is the HA. And density of air is, I have considered 1.2 at normal temperature condition. So if you substitute entire this thing, okay, taking HA is 11.4. See now CD is 0.6. Okay, so CD is 0.6 pi by 4 into D naught square. So D naught square orifice diameter is 15 mm. So 15 divided by 1000 meter square, okay, into 2gh, 2 into 9.81 into 11.4. Just calculate, let's see how much we will get. Okay, so we will get, I'll just calculate, 2 into 9.81 into 10.4 into 0.6 into pi to 0.6 into 15 divided by 1000 square. We'll get 0.095. Get 0.095. This is the mass of air, kg per second. So mass of fuel. Now rho of diesel you have to consider. So rho of diesel is density of the diesel you have to consider is, okay, so check out for density of diesel. Okay, the data is not given, so hence density of diesel consider, so it is 0.5 kg per liter. So if you put it in terms of, okay, so 0.85 kg per liter. Okay, so now mass of, I'll show you here. So mass of fuel is 20 into 10 raised to minus 6 to 0.85 kg per liter. So you know that 1 liter equal to 1 meter cube. Okay, so hence, okay, 1000 fine. So I'll just convert that also. So let's see, kg liter to, yeah, in kg meter cube directly I'll get. So 830 kg per meter cube. So this I'll take it as, so here mass of fuel is 830 that is density divided by time taken. So for 20 cc it has taken 100 seconds, no? Yes, so consider 100 seconds. So you will get 20 into 1 expression minus 6 into 830 divided by 100. So I'll get 1.66 into 10 raised to 4. That means it is 0.00016 mass of fuel kg per second. Okay. Now take the ratio. Mass of air is 0.095 divided by 0.00016. I think, yeah. So here 15 mm. Yeah, here 1 minute. I'll just cross check with the density of air. So density of air is, it is 1.2. Okay, so whatever value we got in the manometer is 9.5, okay, meter of air. Just cross check this. Maybe values are doing something else. Okay, this is directly 95. Sorry, so there is small correction here. It is not 9.5, it is 995. So if you, yeah, so if you connect that 95 directly, you are getting 95 this, not small correction. So if you take 95, you will get 95 into 1.2. So you'll get 114. Yeah. So this is 114. Oh, yes. This is a 114 meter of water. So if you substitute here 114, then you will get square 2 into 9.81 into 114 into zero point 0.6 into pi into 0.25 into 15 divided by 1000 square. Yeah, you will get point double zero double zero. You get 0.005. So if you take ratio now 0.005, so you will get 5 divided by, so you'll get 31.25, the air fuel ratio, 31.25. It's a actually a very higher airflow ratio because it's running under normal condition. Hence, so now if you take brake power, brake power is 2 pi n, RPM is given, and load you have to consider, here, sorry. Yeah. So difference between this 4 minus, this is a kg actually. So 4 minus 0.2, that is 3.8. Now you take brake power here. Again, I'm showing here brake power 2 into pi into RPM I'm taking into 3.8, 4.2, 4 minus 0.2, 3.8, and that 2 pi n two pi n into 3.8 into radius of the breakdown. So radius of the breakdown, I think value 1 minute. So radius of the breakdown is value, I'll just tell you. Yeah, it is 175 mm. So 175 mm. If you consider 175.175 is the meter. So 2 pi nt divided by 60,000. 60,000 is conversion. Divided by 60 it gives watt. Divided by 1000 it gives kilowatt. So if you do this, 2 into 5 into 1500 into 3.8. This is in kg. So hence you have to convert in terms of Newton. So you have to multiply with 9.81. So 9.81 you have to multiply. So into 9.81 into 0.175 divided by 60,000. 1 minute. 2 to pi. Okay. Yeah, you will get 1.024 kilowatt. You will get 1.024 kilowatt. And specific fuel consumption, you already know now. Mass flow rate is 0.0016 divided by BP. BP is 1.024 10 raised to 3 into 3600. If you substitute, you will get specific fuel consumption. Now input energy is mass of fuel. So mass of fuel is 0.00016 into calorific value of the diesel. So calorific value of the diesel, you have to check this. Okay, you can cross check anyway. So calorific value. So calorie we don't want in kilojoule per kg. It is 45,000. Consider 45,000. Just as a demonstration, all these values will be given to you. Kilojoule per kg Kelvin. So if you do this, you'll get 16 into 45,000. You'll get so 7.2. Sorry, 7.2. Okay, kilowatt. So indicated power, you have to, as I said, you have to do from the graph. So for more number of values, you have to do it. So now it's very easy for you to understand. See now in this graph, fuel flow rate kg per hour. So mass flow rate we know, we convert in terms of hour, and for different brake power, I mean different trials. If I give 4 trials, generally in your test we will give 4 trials. You take 4 trials, calculate all the brake power and calculate all flow rate, then you'll get friction power. So here since I'm showing for only one value, friction power I'm not able to say. Okay, you have to extrapolate to the x-axis. Here I am not able to do that. So hence roughly I am considering. Okay, so IP you got brake power you got 1.024. So roughly I'll consider some 40% loss is there. Okay, if I do that, roughly I'm considering, so 0.6 into 1.024, you'll get 0.61. So I'll consider here, I mean your fine. Okay, it is 1.4 into 1.02. Okay, so from your experiment you have obtained around, just I will mention you whatever you have got from the experiment, around 6.3 kilowatt. It's very huge, that means friction power is very high. Anyway, so let's see that later. So this you will get from the graph. Friction power will be very high, maybe around roughly 5.2 kilowatt, something like that you will get. That you have to cross check when we give the 4 number of trials. You will get, because this is from your experimental data I am showing you. Now brake thermal efficiency is brake power 1.024 divided by input energy, Q input, just calculate it, so 7.2. If you do that, so you will get what is the percentage. It's very low, so 1.024 divided by 7.2. So roughly 14.2%. Okay. So similarly, indicated thermal power efficiency, mechanical efficiency, all these things we will calculate. Now indicated power is 6.3 divided by 7.2. And brake power, now it is 1 point, mechanical efficiency is 1.02 divided by indicated power is 6.3. So very mechanical efficiency is very low. 1.02 divided by 6.3. So roughly around 16%. A very old engine, so you are getting mechanical efficiency of this order. Q actual mass of air divided by rho of air. So you have calculated mass of air here, and density of air, if you substitute 1.2, you will get this. Volumetric efficiency also, you can do that. Okay, now I'll go to directly heat balance sheet, which is important for this experimental discussion. Now Q input, the same thing we will get mass of fuel into calorific value. So mass of fuel and calorific value we have calculated. You got 7.2 kilowatt. 7.2 kilowatt. And brake power we have just calculated. The same value I will take. Brake power is 1.024, 1.02 kilowatt. Heat lost to the engine cooling water. This is what now we have to calculate. So mass of water, how much you have supplied, Cp of the water, Tw2 minus Tw1. Now you see this tabular column. So Tw2, Tw1 is this cooling water, 32 minus 27, and mass of water. How much mass of water you have supplied? The mass of water you have supplied is, see here, yeah, mass flow rate is 2 liters per minute. So liters per minute you convert in terms of kg per meter cube. Yes, kg per second. So you have to convert as a flow rate. Then take delta T, Cp is 4.8. Let's see that now. 2 liters per minute, you have to convert this 2 liters per minute. Cp is 4.18, I mean 4.18 into 10 raised to 3, specific heat of water. Tw2, Tw1 is 32 minus 27. So this you have to convert in terms of meter cube per second. Do this, you will get. Okay, so I'll just directly show you directly using this liters per minute into kg per second. Okay, so 0.74 kg per minute. Okay, so now see, now your liters per minute is 2. If you put 2, then you will get 2 liters per minute. You will get okay, 1 liter per minute equal to 0.74. This directly we will use kg per minute. Okay, I need kg per second, right? Yeah, so liters per minute to kg per second. Okay, if I consider this also 0.74, directly we get. Okay, let us consider 1 liter per minute. So to 1 liter per minute is 0.74 kg per minute. Yeah. So let convert. So yours is 2 liters kg per minute. So 1 liter per minute equal to 0.74. So just you multiply this value with 2 into 0.74 divided by 1 minute equal to 60 seconds. So 60. Now you just do this 2 into 0.74 divided by 60 into 4.18 into 1000 into 32 minus 27. Okay, so you will get 515 515 watt So 515 watt means 0.51 kilowatt. 0.51 kilowatt has been taken out by the cooling water itself. Okay. So this is what about the second point. So you have an engine. You have an engine. Now you see the piston moves up and down, and amount of heat is generated. So some amount of heat is taken by the cooling water, which is supplied outside engine head, and some amount of the heat will be taken away by the hot gas. So hence the total amount of heat generated will be taken by some amount by the cooling water, some amount by the exhaust gas, and some amount to actually convert in terms of brake power. And still some amount of heat will be there because there will be cooling rings and cooling oil, I mean engine oil. To that also some amount of heat will be taken out, but those are all difficult to account. So hence those are all called unaccounted heat. You can see in the heat balance sheet the amount of heat taken by to generate the brake power, amount of heat taken by the cooling water, amount, this is what cooling water QW, amount of heat taken by the gas, this is what QG, and unaccounted heat which are all there in the engine is unaccounted heat. So this is how heat balance we have to do it. Now we have done first one, what actually amount of heat is generated we know, and how much it is taken for the brake power we know, and how much for the cooling water we have just calculated. Now let's calculate gas. So in the gas you have to calculate MGCP. You have to calculate MGCP. So using the calorimeter. So you have the calorimeter. In the calorimeter, amount of heat collected by the water is equal to amount of heat lost by the gas. Okay. So a mass of water and CP, we have just seen here in the calorimeter 3 liters per minute. This 3 liters per minute, you convert it in terms of second. CP of the water, TW2 minus TW1 is given here. The calorimeter, see here, it is what calorimeter values are, 28 minus 22. If we substitute here, and MGCP is unknown, so MGCP is unknown, and TG minus TG1, that is the calorimeter temperature, calorimeter gas temperature. That temperature is, will tell you, okay, this is exhaust gas temperature, and that value generally it will be of around 2 to 6 degrees Celsius. There will be variation, and those values you can consider for the calculation is okay, the amount of gas entering the calorimeter and leaving the calorimeter. Okay, so here one point is you can directly consider this temperature 370. So 300 is leaving, leaving is 300, and entering is yeah, leaving is 300. This temperature is 300. And leaving is 70 degrees Celsius. If you take this, then you will get mass of water, TW2, TW1 is given for the calorimeter 28, 22. So this is 28, 22. Once you do this, you will get MGCP. This MGCP is substitute here, and the gas leaving here, gas leaving is okay. Yes. So this is with reference to the atmosphere. So this is actually TG1. The gas leaving is 70 and atmosphere temperature is 25 degrees. If you consider this and MGCP you have calculated from this calorimeter, then you will get heat loss heat loss loss to the gas. So this is around you will get around 4 point. I'm just writing the calculated value. you are getting around the huge value you will get. Around 4.3 kilowatt. Okay. Yeah. Now unaccounted is you take total heat input is 7.2 minus 7.2 minus BP is 1.02 plus water is water lost is 0.51 plus 4.3. If you do this, you will get 7.2 minus 1.02 plus 0.51 plus 4.3. You will get 1.37 is unaccounted heat. So all these things you have to put here. So the total heat input is 7.2 and by BP is 1.02. What is the percentage? You have to calculate. And water 0.51 and gas is 4.3 and unaccounted is 1.37. If you calculate this, you will get directly 100%. You work out the percentages. And this will become totally 7.2. If you add up this, this will become 7.2 total heat input. So this is how you have to draw the heat balance sheet. Okay, I have shown for one value, and please work out for other values which we will give in the for your test. We'll give different trials. Through different trials, you have to use William Lines method. You have to calculate friction power. Then automatically all these values you will get. You just keep substituting all these values and substitute back, and that we will evaluate. I hope this gave some insight, even though virtual, but you got some very good insight about how to do the heat balance sheet calculations. Okay. If you have any questions, feel free to ask me and I'll answer your queries. Thank you.